It's my pleasure to introduce our keynote speaker this morning, Dr. Joelle Pineau. Joelle is a professor at McGill University, and she's also the head of Facebook AI research in Montreal. Her research focuses on reinforcement learning and decision-making algorithms and applies them in complex domains such as robotics and healthcare, conversational agents. And she's going to talk to us today about 3 underappreciated R's of reinforcement learning: reproducibility, reusability, and robustness. Please welcome Joelle.
Good morning, everyone. We will take... Great. It's a pleasure to be here this morning. Thanks to all of you who got up early to be with us this morning. This is a bit of a slightly different model of a talk, perhaps. It's not so much a survey of a body of work, but it's really about sharing some of my reflections on this topic, essentially why these things are important, why we need to incorporate notions of reproducibility, reusability, and robustness in our research, in the practice of the science that we carry out. And it's also not only about RL. I think there are lessons here for those of us who are working across fields in machine learning, learning representations, and so on. Of course, I'm going to draw many examples from RL because that's where I do most of my work, but hopefully there will be useful areas of reflection for all of us together. Before we launch into this, perhaps spend a moment thinking about what we mean by reproducibility. The National Science Foundation has proposed the following definition, which I think is a good starting point for our discussion this morning. So reproducibility refers to the ability of a researcher to duplicate the results of a prior study using the same materials that was used by the original investigator. And perhaps most importantly, the point that reproducibility is a minimum necessary condition for finding to be believable and informative. And this doesn't come strictly from the perspective of computer science or machine learning, but is really, I think, a notion that applies broadly across the different disciplines of science. Many of us have been hearing about this notion of a reproducibility crisis. The journal Nature conducted a study in 2016, still quite recent. 1,576 scientists were asked whether they believed there was a reproducibility crisis. From that group, 50% said they thought there was a significant crisis. 38% said there was a slight crisis. So quite high level of awareness across the disciplines. Follow-up question asked them whether they had failed to reproduce an experiment. And then they divided by subfields. It's written a little bit small. In computer science isn't there on this graph. At the top of the graph, we have the chemists. Below that, the biology, followed by physics, medicine, earth and environment, and then the other. I guess we fall under the other. The dark red line here is the cases where someone failed to reproduce an experiment from somebody else, presumably from another lab. That goes beyond 80% if you're in chemistry, and around 78% if you're in the biology. The lighter line, the pink line here, is the case where you failed to represent one of your own experiment, presumably from your own lab. Again, quite high, above 60% for both biology and chemistry, a little bit lower for physics, medicine, earth and environment science, though perhaps they're a little bit less candid about some of their issues. I was curious to see how that might extend to machine learning. So back in December, I was in a workshop, and I asked colleagues in the workshop to sort of play along this same game with me, asking them whether they thought there was a reproducibility crisis specifically in machine learning. And in this case, about 80% of them thought there was either a slight or a significant crisis. And so in my mind, there's definitely reasons for us to be thinking about this. There's reason for us to be talking about this. And hopefully there's reason for us to take action and see how we can do better in this respect. So quick hands up, who presented a work this week at ICLR? Maybe a poster, a talk, don't be shy. You should be proud of the work you did. Great. Keep your hands up if you shared code and made sure the data set were available. Excellent. So a criteria for reproducibility. An article about computational science in a scientific publication, it's not the scholarship itself. It is merely the advertising of the scholarship. And so this week we came together in Vancouver and we did a lot of advertising for our science. And some of us are very good advertisers and can tell an excellent story, but it doesn't quite rise to the level of what we would like. And so our friends Buckheit and Donahoe have argued, going back to 1995, and I think these words are true, that the actual scholarship is the complete software development environment, the complete set of instructions which generated the figures. And so I think one of my messages today is to encourage us to embrace that definition. I'm not saying we need to neglect the advertising of the science. I think the communication that goes along with the scholarship is incredibly important. It's important within our community so we can understand the ideas. It's important so we can share the ideas, so we can collectively move forward. And it's also important to communicate the results outside of the field. But we shouldn't lose track that this only makes sense if we are actually also engaging in the collective enterprise that is the scholarship itself and sharing the artifacts of that together with this. Let's look a little bit more closely perhaps at reinforcement learning, because this is my area of research. I started working in reinforcement learning in around 1999, published my first paper in reinforcement learning in 2000, paper on using MDPs for dialogue systems. I haven't strayed too far in the years since. And in those days, you know, it was the days when as a grad student you could publish one paper a year and be doing very well. I published my first NIPS workshop paper also around 2000 in a NIPS workshop on reinforcement learning. There were 35 people in the room in those days. I was also the only woman presenter in those days. Some things have changed, others have changed maybe a little bit less. Since then, 2016, last year for which we've collected this data, we had about 13,000 reinforcement learning papers published. So it seems our community has done a lot to increase our advertising footprint. That's a lot of results coming out. And in some cases, it can be a little bit difficult for someone entering the field or even someone trying to keep up with the field to really get a firm understanding of which of these 13,000 papers are really moving the needle in terms of our knowledge and in terms of our understanding of the world. Many of them are very impressive. Perhaps the one that got the most attention, truly impressive result, is the work on AlphaGo. Came out in 2016. Really impressive result using a mixture of reinforcement learning and deep learning techniques, showing that an AI system could actually beat the best Go players in the world. Of course, this was built on several years of research from Google DeepMind researchers as well as researchers outside, facilitated by the sharing of information over the years. And as reinforcement learning researchers, we have to say we were quite happy because for the first time in almost 20 years, we could stop citing the TD-Gammon result as the single most outstanding result in reinforcement learning. So really quite an exciting system. And of course, I would say the advertisement for this work was on the scale of the achievement, including front page news in Nature, several media, perhaps even a documentary movie, I'm told. And if you actually went and read the Nature paper, in the appendix there was actually a very high level of detail in terms of what was done, how things were implemented, and so on. But in terms of really having a blueprint for the research, in some sense, it feels like it fell a little bit short for some of the other teams doing that. It was a very high mountain to climb for many other teams wanting to replicate this work. The accessibility to the expert games that were used to train the initial policy were not necessarily easily available for all of us. The development of the code, of course, is a huge effort. The search over the hyperparameter space and the computational requirements necessary to train the system are really hard to replicate outside of the team who did the initial work. Not to mention, I guess, the logistics and the financial cost of setting up a series of matches against Lisa et al. And so I think in many cases, it's important to think of how do we facilitate that road. Once someone has climbed to the top of that mountain, one research team has done it, how do we make sure that we leave the path open for other teams to follow that path? And how do we incorporate this aspect of the research process in the projects from an early stage? It's often a lot harder once the project is finished to do it, but how do we set it up from the beginning of the project? Of course, to be fair, right, this project and many others are not the first time we were left without a fully executable blueprint. Perhaps the most famous example of this is Fermat's last theorem, dating back to 1637, left casually in the margin of another paper. History has it that Fermat said that there just wasn't enough space in the margin to lay out the full proof. And I understand paper was very expensive in those days, perhaps on the level of GPUs these days. But as a result, right, we spent the next 358 years looking for a proof to this theorem. Fortunately, our misery was over in 1995. Andrew Weil published a proof, which meant that generations of young mathematicians could work on something else. And it also meant that in the process of producing that proof, we discovered many new things about mathematics that perhaps we would have known a lot earlier had Fermat spent the time to write down that proof somewhere. For those of you who are curious, nowadays, the longest standing math problem is actually Goldbach's conjecture, dating back to a mere 1742. And so there's still many of these open problems in other fields. The Guinness Book of World Record keeps track of these things. It doesn't in the computational sciences as far as I know, so let's try to stay out of their radar for now. Mathematical conjectures aside, I think for those of us who've had the good fortune to read a paper that really inspires us, a paper that perhaps contains a model, an algorithm that we think can potentially be used to solve a real-world problem, it's sometimes a little bit daunting to think of all that we are going to have to do to take the idea in that paper and make it work to solve that real problem. And so there's really a sense when we are able to do that path, either because it was facilitated by the original inventors of the idea, or because with our own team we're able to take that road to actually get the work working and actually see that it's realized fully and that the potential as advertised makes a difference in solving a real-world problem. There's a certain sense of satisfaction that comes from that. Let's go back to the question of reinforcement learning, because as a field, reinforcement learning, we've had a lot of discussions around what are some of the best practices we need to put in place to allow this. In contrast to our colleagues who work primarily in supervised learning, we don't have the luxury of exchanging data sets, static data sets, with a set of IID examples. We really need to interact directly with the dynamic environment. And so there's been a number of platforms and tools that have been used by the community widely, and this, I would argue, is an essential part of enabling reproducibility of results. One of them, for those who are a little bit more adventurous, is the robot soccer community platforms and so on. In the robot soccer community, there are some extra challenges. You're dealing with the physical world, with robots, partial observability. And for many years, they had a rule that after the competition every year, everyone had to release the code, such that the barrier to entry for the next year was sort of even grounds for everyone, which I thought was a very nice community practice. The Mojoko simulator is extensively used nowadays to test continuous reinforcement learning algorithms. The arcade learning environment has propelled our ability to do deep reinforcement learning in many ways by setting a very high bar in terms of the complexity of the task, particularly on the perceptual side. And more recently, in 2017, the ELF platform was released, enabling multi-agent strategy games. This is sort of a plug-and-play environment in which you can actually instantiate multiplayer games in a very flexible way. All of these available quite easily. I believe Mojoko requires a license, but Arcade Learning Environment and ELF are freely available, downloadable for everyone. And so I think my main message today, and what is sort of the thing that ties the different pieces, is the following. We really need to have some reusable material, whether they be software, data sets, experimental platforms. This reusable material is going to enable us to reproduce scientific results. And if we are able to reproduce scientific results, then we're going to have much higher confidence in the robustness of our findings, whether they be specific numerical results or actual conclusions from our study. Let me take a few minutes to dig more deeply into this question of RL, and specifically the robustness of the results in reinforcement learning that ties really into my message today. And so I won't talk about deep reinforcement learning, its full generality. I'm going to focus, for the purpose of today's talk, on the setting that is the policy gradient methods. So in policy gradient methods, a policy is a behavior strategy for our agent. So if you're dealing with a robot, it's the control strategy of the robot. And if you're dealing with a player in a computer video game, it's the actual behavior of the player in that computer game. And so when you're doing a policy gradient method, you assume that the policy of the agent is parameterized by some parameters. In this case, I'm using theta to denote the parameters of the policy. And the behavior is trained using gradient descent techniques. That behavior is trained using a policy gradient equation. In this particular case, the equation incorporates the expectation over the state distribution, what are the states that are going to be visited if we carry out this behavior, as well as the value function. So what's the expected return of taking this behavior in this particular state? And that can be done either in an on-policy way, where you actually collect the rewards and the returns by following the policy that you're trying to optimize, or it can be done in an off-policy way, where you actually collect data from different behaviors and then try to evaluate specific behaviors and do gradient with respect to specific behaviors. The reason we focus on this is because there's been many policy gradient papers over the last few years. At the top 4 or so were papers that are probably some of the most cited for the last couple of years. And below that, I quickly scanned through the ICLR 2018 proceedings and literally just pulled out papers that had been accepted this year and that had the word policy in their title. So I apologize if I missed your policy gradient paper because you had a more original title. There may be more than this, but just from a quick scan, I dragged out 7 papers. I'm not going to talk about these papers. The authors who are here today are much better placed to do that. Read their papers, visit their posters. The thing that I'm really pointing out is that many of these papers are actually all using the same baseline algorithms. There's a set of common baselines that have really been used widely to compare any of these new algorithms. And these baselines are very important because as the volume of paper is large, right, there's like at least 7 papers, and I checked all of these, that they were using the set of baselines I'm going to be talking about, and maybe there were more. It's important that we have a good understanding of what are the right sanity baselines, because we can't expect these papers to compare to each other. They're all coming out in the same cohort. And so some of the most used baselines are the following one: TRPO, excellent standard, PPO also quite widely used, DDPG, and then actor is a little bit of a variant on TRPO that also has become quite standard. Perhaps some of you may be using actor critic, A3C, A2C, also widely used. I won't include them in my analysis for today because they tend to perform a little bit less well than these ones. They're very fast to run but tend to give lesser performance, so I'm going to focus on these for the purposes of today's talk. And so let's look a little bit at the robustness of these baseline methods, these policy gradient methods. And I don't want to focus so much on which method has which characteristics. I really want to focus on how we compare these methods and how we use them to establish baseline and to get evidence of the efficacy of our methods. And so this is in the context of the Mojoko simulator. For those of you who've never used Mojoko, you have these little characters moving along. This is the half cheetah. It's a half cheetah because it's like half the body of the cheetah, just 2 legs of it. And you essentially have to train a policy to control the joints of the cheetah such that it can actually move without falling as it moves around. And so for this particular half cheetah algorithm, we train the 4 baseline algorithms. We'll call them algorithm 1, 2, 3, 4, maybe identify them by their color. And for this particular setting, algorithm number 1 seems to be doing quite well. And so from this result, if you're trying to propose a new policy gradient method, it seems reasonable to use the red algorithm as a good baseline to compare your algorithm to. Now, if I do the same thing in 2 other Majoko environments, the hopper on the left, the swimmer on the right, the results look really different. All of a sudden, the best baseline seems to be algorithm blue. Now, it shouldn't be that surprising that different algorithms are better for different domains. But what surprises me is the fact that within the Majoko simulator, the tasks are actually quite similar. Right? They're reasonably low-dimensional joint space description of the state space. They have few-dimensional control actions. They're continuous, relatively smooth dynamics. And so you would expect certain algorithms across these different domains to behave similarly. But the results we see are really quite drastically different. On the half cheetah, the red is doing much better than the others. On the swimmer environment, it essentially completely fails to learn. And so it makes it a little bit difficult for us to know what are the right baselines to use. We want to include valid baseline when we're sending a paper for review or publishing a paper. At the same time, it gets a little bit tedious to try all of the algorithms on all of the domains just because they have such variable performance. We went digging through this a little bit further. We thought, maybe our implementation of some of these isn't the best. So let's see who else has implemented these algorithms and if we can do a little bit better. So quickly, I just did a quick screen grab, a Google search on GitHub TRPO. And then I had a whole list of software packages that appeared. I should be really excited about this. I'm advocating for distribution of software packages, sharing of this code. So there's at least 10 of them that came up very quickly, top of the search. And then I ran these code bases, all of them on TRPO. And I got really drastically different results. Again on the half cheetah task. So then I'm a little bit at a loss for what to do. Not only do I need to run all the baselines, I need to consider all the implementations of all the baselines on all of the problems that I might want to test my algorithm on. Whew. It's not just TRPO. I'm really not trying to say that TRPO is any more brittle than others. To this, we did the same exercise with DDPG. One of the implementations of DDPG clearly superior to the others. And so there's some significant differences between these, and sometimes very hard to know what these are. We went digging a little bit more about what kind of factors could explain these differences. We started looking at something like the structure of the network that is used to represent the policies. These are neural network structure for the most part. Because it's a policy, they tend to be feed-forward neural network with a few layers. On the top graph, I vary the number of units in the layer, and I vary it from 2 to 3 layers. Drastically different results come up. On the bottom, I vary the actual unit activation from a ReLU to a TANH and so on. And again, slightly different results. In this case, especially as the learning progresses. On the x-axis, I have the time step of learning. Big effect, reasonably large space in terms of hyperparameter configuration. And furthermore, it's not always useful to look at a single hyperparameter in isolation. When we start looking at the interaction, the interplay between these hyperparameters, we also notice some significant effect. In this case, we're comparing on the top the different reward scales. You're doing reinforcement learning, there's a reward. Are you going to rescale your reward between 0 and 1, between 0 and 10, between -1 and 1? Depending which rescaling you use, you get really different results. Those of us who started doing reinforcement learning back in the days where we were doing tabular grids are thinking like, we always thought we could do linear rescaling of the reward and things were fine. It turns out when you plug this in with a high-dimensional nonlinear function, that doesn't hold anymore, so the rescaling has a major effect. The rescaling interacts top graph versus bottom graph. I'm actually varying whether you're applying layer-wise normalization or not. Again, completely different results pop up. Now remember, all of this which I'm discussing here aren't all the design choices that apply to your own algorithm. These are all the design choices that have to be considered and optimized for the baseline algorithms to which you're comparing your fancy new algorithm. And so I think one thing that happens in many cases is that we're not necessarily as motivated to find an outstanding performance in our baseline algorithms as we would be for our very own method. And given the susceptibility of the approaches, not just one of them, but several of them to this, there's a lot of challenges that come with this and a lot of responsibility on our part to be very thorough in our experimental methods if we want to publish results that we think are actually sound and robust. We went digging, we sort of stepped back from all this, and we actually went really looking at how we should measure the performance of the learn policy. So in reinforcement learning, what we care about is measuring the expected reward over the trajectory, this notion we call the return. So it seemed reasonable to think of looking at the average of the empirical return you would obtain. So I'm back to having my 4 algorithms 1, 2, 3, 4, and fortunately enough, we didn't have to look too far to figure out the formula for doing that. We calculated the average return over the test trials, and we also thought it'd be good to think about the confidence interval. In this case, we're making the assumption that the returns are distributed in Gaussian fashion, which, if you have enough sample, probably isn't too bad. And the only question left open is really, how do we pick n? Now, if you're in supervised learning, maybe you start things out with the MNIST data set. I think 10,000 examples in the test set for MNIST, I think. Here are the number of test samples that are used in some of the top deep reinforcement learning papers of the last couple of years. None of them get up to 10. Some of them take 3 trials, some of them take 5 trials, some of them take the top 2 out of I'm not sure how many, or top 3, top 5. And I'm quite sympathetic to this because these experiments are long to run and they're slow, and you've done the hyperparameter optimization, and so you have to consider many cases. But let me just sort of illustrate what happens. In this case, let's say, just 10 runs. And you're comparing the results of your 10 runs. On the x-axis, again, I have the number of examples. On the y-axis, I have the empirical return for each of these runs. And let's say the blue line, the flat line, is some baseline, some other baseline that you're trying to beat. We have 10 runs, and this is what the results look like. And when a student comes and sees me with this kind of a plot, I say, yeah, okay, your algorithm is learning. We might not be done in terms of showing that our results are better than the baseline. Now, if the student picks the top 3 runs and shows me this plot, then we might be thinking like, yeah, we've got a trend here. Let's write the NIPS paper, right? And so there's 2 things that happen when you look at just a few top results. The first thing that happens, of course, is you have a strong positive bias. And the second thing that happens is you have a much smaller variance. And when many people publish paper with this over a long period of time, there's a certain set of practice that gets set into place. So one of my mission has been to sort of slightly change the course of the field in this respect. Maybe one last example from policy search is the following one. In this case, right, we have the orange algorithm comparing to the blue algorithm. There's 5 runs of each, so it seems a little bit better than if you had just 3. They're not top 5, they're actually just 5 runs. Assume this is a really expensive thing to run. It took a long time to get those 5 lines. And so based on this result, you may think that you've got like a pretty clean difference between the 2 algorithms. And if the student comes presenting these results to you, you should, of course, ask as many questions of the good results as you ask of the bad results. So when you ask the student, what did you run? What is the blue line? What is the orange line? Well, both of them are the exact same TRPO code with the best hyperparameter configuration. And the only thing that changes is actually different random seeds were used for the blue line and for the orange line. Okay, I think I've made my point. Let me back out and say why I care so much about this. 30 years ago, perhaps we didn't care. Those of us who were doing reinforcement learning, or even 20 years ago. There was a really widespread agreement at that time that RL was just too hard, and it wasn't going to be used to solve any problem anytime soon. We could play backgammon, and we could play backgammon, and that was about it. And now we're at a different stage. There's really the sense that we can solve tremendously hard problems. The AlphaGo results showed us this. It's not the only one. There's been application of reinforcement learning in several areas. We're on the verge of being able to apply reinforcement learning to problems that really matter in healthcare, in terms of treatment design and discovery, in terms of managing our resources, our natural resources, in terms of managing our energy systems, our financial systems, crucial systems to our lives and our societies. And reinforcement learning is a beautiful paradigm to cast many of these important decision-making systems. And we have powerful algorithms to do that. And we have a lot of papers presenting a lot of algorithms for doing that. But unless we really up our game in terms of how we characterize our results, how we share those results, and so on, there's a potential that we will have a gap and that the methods won't fully be able to tackle the problems at the level that we expect and at the level that society expects us to deliver. So I want to bring us back in the last 5 or 10 minutes that I have really to why I entered this field and why many of you, I believe, also entered this field, which is science really as an endeavor to understand and explain. Science isn't a competitive sport. Science is really a collective institution. We are embarking on this together, and together we aim to produce more and more accurate explanations of how the world works and how we can solve important problems for this world. And there are no shortage of important problems. And so I think we have to all pitch in once in a while. There's many reasons to take a different approach that treats science a little bit more like a competitive sport. There's many incentives to do so. But I think we really have to, once in a while, step back and say, think of what we're doing, how we're doing it, what we can do for that. Perhaps one example, a project that was taken on recently by some of my colleagues at the Facebook AI Research Lab. Over the last few months, a group of engineers, researchers, led by Wandang Tian, have worked really hard to produce an open source Go playing bot. It's called ELF Open Go. It's actually available as part of the ELF infrastructure. It's there to download anytime now. It includes both code to train up the bot. If you decide to use that part of the code, you will probably need 2,000 GPUs running for 2 weeks and a sizable budget to go with it. It also has pre-trained models. And these pre-trained models can actually be run by the Go community. There's been a lot of interest, I think, in Go players to have access to that. It can be used by the machine learning community. The code is built in a way that it's actually decoupled and highly reusable for other games because it was built in this ELF infrastructure. And so the goal wasn't necessarily just to build the best Go bot out there. Actually, there's been an example of a tremendously effective Go bot, but really to have one that is of high quality and that people can start playing with. And so please go ahead, check it out. We've sort of been testing it just to make sure that the quality was quite good. Over the last couple of years, we played against a number of top 30 Go players, thanks to the Korean Go Player Association that were very nice in facilitating these games quite rapidly. In all of those games, we actually ran the pre-trained models on a single GPU. Again, thinking of how do we build tools that are reusable by people that Go player can afford and probably run. 80K rollouts running on that GPU player, about 50 seconds per move for the bot. And so it's actually quite scalable. It's the kind of thing that most of kind of architecture, infrastructure, most of us have access to. We were quite pleased with the performance of the bot, I think, internally. I think the Go players were promised a sufficient amount of money that they were motivated to win against the bot. Also has good performance against some of the other online bots, such as Lila Zero. I won't go in much more detail. I think it's just an example of the kind of project that people can take on, not because it's necessarily uncharted territory, but because it's actually a resource that's really important, we think, for the community, both the machine learning community, and in this case, the community of Go players. Let me switch gears a little bit and talk about one last initiative on which I've been working over the last few months. Some of you have probably heard about this. This is the ICLR 2018 Reproducibility Challenge. So I thought it was wonderful that I had the opportunity to share with you some of that experience. The challenge is something that we launched within a graduate course I was teaching at McGill. I teach a course on applied machine learning techniques. I had last fall about 180 students in that course at the graduate level, and I needed to keep them busy, give them a final course project, and I thought there's like all of this energy that's going to go into a final course project. Can we somehow harness that talent energy towards some good for science? And so I put them to challenge to pick a paper from the ICLR submission site. Open review made it very easy for them to have access to a whole list of papers. Pick a paper, aim to reproduce some or all of the results in the paper. It started within our graduate course at McGill. I sent out an invitation via some mailing list to colleagues all around the world. 10 different graduate courses in machine learning showed up, said, we will do this also. So there were people from Poland, from France, from Israel, several groups in the United States also, who joined us in this challenge. In total, 124 teams or individuals committed to reproducing a paper. 95 papers from ICLR were subject to this exercise. And the participants, because of the timing, were actually invited. Most of them wrote a report to submit to their course instructor, but they were actually invited to prepare a blog post version of it to submit on the open review as voluntary comments, such that the authors and the reviewing committee could actually perhaps consult what they had to say about the paper. And after all this was done, I actually ran a survey of participants and authors and so on to see what they thought was the conclusion of that exercise. So in the survey alone, I had 54 people, respondents who were challenge participants, 30 who were authors of ICLR submissions, and 14 others who were either random volunteers. The challenge was open to anyone who wanted to sign up. It wasn't restricted to people taking these classes. We asked them before the challenge, do you think there was a reproducibility crisis in machine learning? The numbers don't vary that much from my 20 ML experts. 49% saying there's a slight crisis, 22 a significant crisis. I asked them afterwards, and about half of them said their opinion hadn't been changed. In blue, we have 30% of people who were more convinced there was a crisis. We asked the students, were you successful? Did you manage to do this? 55% of them were able to reproduce some of the work. 33% said, yes, we could do most of the work. Was it hard? Yeah, it was hard. Reasonably difficult for 40%, very difficult for 22%. In some cases, there's a gap in terms of computational availability. Fortunately, Google offers us a generous amount of Google Cloud credits, and about 50% of the participants made use of these credits to be able to facilitate the reproducibility of the paper. 43% of participants actually communicated with the authors, either via open review, email, GitHub. A good number of them said they were able to maintain anonymity through that communication process. And we asked the participant, do you trust the results of your work as communicated to the authors? And most of them in red were moderately confident, or in blue, highly confident. Then we asked the authors, do you trust the result of the reproducibility results? And actually, 69% said yes. 15% said not sure, and 20% were a little bit not really sure that the authors had really understood what was said. 20% said basically that the feedback showed a poor understanding of the work. Perhaps that's not that far off with what we think of what the reviewers' comments are. We asked the authors, do you plan to update your submission based on feedback from the challenge? 61% said yes. Either we will change something in the paper, we will release code. This has prompted us to essentially change what we were reporting. And roughly 30% of the papers that were involved in the challenge were accepted eventually at ICLR. We weren't able to measure if that was a factor in the decision, but certainly based on the author's response, we can presume that it was helpful in terms of improving the quality of the scholarship. We asked all of them, what do you think are the most effective mechanisms to encourage people? 46% said include it as a course project, 36% said put an open call, give out prizes, certificates. So we're looking at that. 7% said assign some reviewers the task of replicating the work. So if those of you who are reviewers, it seems like probably that's not going to be on your to-do list for next year. Finally, we asked the authors, if you had the option in ICLR 2019, would you elect to have your paper included in the challenge? And 79% said yes. Many comments saying it's great feedback, a scientific work should be reproducible, and so on. A few of them pointing out, a little bit less enthusiastically, that of course the reports are subject to high variance, as is the reviewing process. And so I think there's some things we might be able to do a little bit better. So let me wrap things up. I'm out of time this morning. I want to finish with a message of what you might be able to do. I think with these kinds of issues, there's many reasons not to spend time, effort, or money on this. It's not very glamorous in many cases. But I want you to remember that we're really in the business of conducting good science and expanding our knowledge. We're not in the business of advertisement. We want to understand, and we want to share our understanding with the community and with the world. And so in that spirit, please try to contribute, try to take action and see what might be ways that you can contribute. I am here only to present the work of a community of contributors. So please take a picture of these guys and these ladies who have been fantastic contributors to this. The work on RL reproducibility is almost entirely the work of Peter Henderson, Riyashat Islam, outstanding graduate students. I had the good fortune to work with Genevieve Fried, Rosemary Key, and Hugo Larochelle on the Reproducibility Challenge. There's the whole team on the ELF Open Go that have worked really hard in the last couple of months on this, and the students of the Reasoning and Learning Lab that continue to inspire and challenge me every day. Thank you very much.
Great, we have time for a couple questions. There, and there, and there.
Hi, thank you very much for this magnificent talk. We are all here for science, but most of us has more than a single hat on our head. The second hat is probably a commercial company that stands behind us, and this company pays the money, feed us, pays for all the resources, all the labs, and they don't really necessarily want everything to be reproducible to the last bit or to the last pixel of the graph. How do you react to this contradiction of interests?
In many cases, there's competing interests, right? And this is one of them, but there's several others. Some of my students in my course said, well, I have a choice between working 60 hours on your project and failing all my other courses or balancing things. I think there are many competing interests, and where we stand on this is a very personal question. I think my personal view on this, and I will not try to tell everyone that it must be theirs, but is that there are ways to work with industrial partners and companies that can be compatible with your objectives of pushing science, but it may require that you choose which partners you engage with. And in often case, also once you are in the industrial environment, there's a way to affect change. But then you have to pick which company you work with and how receptive they are to you affecting that change. And that is sometimes a very difficult uphill battle. And so I think you have to make those choices. Many of us nowadays are in a position that we have these choices. Those of us with expertise in machine learning these days. And so we have the ability to work with industrial partners who we believe will support good science.
Over here. Yeah, thank you very much for this talk. I fully agree with all of your points on reproducibility. I think it's definitely underrated. I'm wondering about incentive systems that we can set up to actually make authors make their work available. So one thing there is out there is a European conference on machine learning actually has an option to flag papers as reproducible research. That could be something that could be done in our communities too, and it's not required, but it gives papers a significant boost. And if a paper is flagged as such, then reviewers can also check and are encouraged to check. Don't have to check, but often people do check. That is one option, but I'm thinking about, would be curious if you have other options in mind. Thank you.
Yeah, I think having that information be readily available is definitely useful. GitHub has their star system and so on, and having that built in to some of how we archive the work can be really useful. That's part of why we decided to launch the ICLR challenge with ICLR because it was using open review, because it made it easy to have it tracked. So now if you go on the open review comment thread, you can actually see the comments that were left there by participants. You can see what they highlighted in terms of the challenge for that particular paper and benefit from their knowledge. So I think, again, having a way to share that information is really important. How do we, the other part of the question is, how do we set up the incentives that people want to spend their time, their energy, eventually their money on doing this? And in that case, I think we're still really at an experimental phase. That's why when I wanted to do the challenge, many people told me this was a really bad idea. It wouldn't work. The reports were going to be of such crappy quality that it was going to completely, change the review process and the decision-making process. I don't know if anyone feels like the quality of paper at ICLR this year was negatively affected by the challenge. I hope not. The authors that we surveyed said that they thought it was actually a positive contribution. But I think we're still exploring the right mechanisms, and I don't pretend we have all the answers of how to do it. I would love for some of our major conferences to go to a model where you can only submit the paper if you're submitting the code. And so I will be having discussions with some of the leaderships of these conferences and seeing what we can put in place to do that in a relatively short order.
I'd like to thank you for a very interesting, informative talk. I think that the message is a personal one for all of us, and that your insights were good. There's reason from the things you've shown for us to be skeptical, not just of other people's, but our own work. So can you maybe come up with a list of personal practices each one of us can try to incorporate in terms of our own science to improve the situation?
Mm-hmm. Some of that will come from my personal experience, which is more on the experimental LRL side, right? And really it's about, for me, always, asking as many questions of the good results as you do of the bad results, really documenting carefully what are all of the steps that you took both for the baselines and for your results, for example, in terms of hyperparameter optimization, keeping track of all of the pieces that went into the work, rerunning your results, right, in the few hours before the paper submission. There's many times you run something 4 months before, maybe 4 weeks before, maybe 4 days before, and then things happen to your code. And what you have on the last day of submission in the paper doesn't match the code, and the code doesn't match the figures that were generated before. And so being really rigorous and diligent. I think there's no magic solution except rigor and hard work.
I think we can do one more quick one over here.
So you mentioned that on open review, you can see the reviews that the reproducers put. Is there anything that shows prominently, yes, this has been reproduced, like a little flag at the top? Green flag, yes, it's been totally refused. Like yellow flag, sort of. Red flag, no, we couldn't. And maybe have multiple flags for each of the reproducibility attempts. Mm-hmm. Maybe have a table that says, is that something that would be possible?
What you say actually brings me to a point I sort of overlooked, right? It is rarely the case that a work is like reproducible or not reproducible. It's not a binary thing. And so having a small number of flags might be a little bit difficult. Often what happens is part of the results have been reproduced. In the other case, maybe we weren't able to do it, but we don't know why. We didn't have the resources, we didn't have the hyperparameters. So it may be, complete, incomplete, but the different level of completions are hard to mark with good precision. For now, I think you have to read the text, and the text tries to be pretty specific about it. In some cases, there was actually responses from the authors and quite a bit of exchange, and so there's no sort of easy way to bring it up. But in future iterations, we may wish to think about this. Also, a few of the papers were reproduced by more than one team, or were attempted to be reproduced. So in this case, you can compare the results from different teams. I think a couple of the papers there was up to 4 teams that tried some of the pieces of the work. So, yeah.
All right. Thank you very much, Joelle.
Thanks.